path analysis and structural equation models. And the goal I have with this is that in 30 minutes, you'll know everything you ever need to know about path analysis and structural equation models, and you'll probably just submit articles straight to Science, the journal Science, and publish probably 1 or 2 articles a week. Or if we don't get that done, at least maybe you'll have an idea of what it's about and whether you want to try to learn more about it. So I'm going to share screen here in a second, and I'll go back and forth, but I'll cover the slides, and let's see, Luz or Peggy, I think we're able to post those to the Google Drive that was set up for these sessions, and it may also be sent to you by email. So they should be available to you one way or another. And I'll go ahead and share screen for now. Let's see, somebody's got to let me share. I'm not. So Luz, I think you may need to.
Oh, I see. You're the host now.
Okay, so let's see. Do we have slides up? I'm just going to test a few things. So that should be a set of slides. This should be a whiteboard.
Yes.
And back to the slides. This is something else. Okay, everything seems to be working.
Mm-hmm.
So what I'm going to try to do is structural equation modeling is a pretty complex topic. Normally, you'd need to take a full course in it to even become acquainted with it. So I'm not trying to do anything on that order, but I'm trying to give you enough of a flavor that you would have some idea whether you're interested and want to learn more. And then I'm also going to try to point out that it's worth learning something about structural equation modeling, even if you never do it. And the reason for that, I think, will become clear. But so what I'll try to do, give you some ideas about what path analysis is and what structural equation modeling is, how do those two relate to each other, some of the benefits that these methods can provide to you when you're trying to do your work, also noting some of the limitations. And for example, they can't be used to make a good margarita. So they're just things they can't do, as well as things that they can help with. And I'll zero in on a handful of things that have pretty wide appeal. And one of those is to be able to decompose effects. You may or may not have heard of that expression before, but often we are curious about how a given variable affects another variable. And within this framework, that may involve a number of subcomponents. And the framework allows you not only to identify the subcomponents, but also to put quantitative estimates, including confidence intervals around those components. I'll also highlight that path analysis and structural equation models make measurement assumptions that are often hidden and kind of basically, I don't want to say ignored, but let's just say they're not in the foreground. It moves them to the foreground and makes them explicit. So if you do structural equation modeling, you must explicitly think about your measurement model. And often we get in habits where we don't think very much about the measurement model that is implicit in the work that we're doing. The same thing applies with regard to causal assumptions. We often estimate regression equations with the notion that they're telling us about how two variables are connected, two or more variables are connected. And we may be careful about how we make causal claims, but often the regression is structured in a way that it at least allows for us to think about causal claims. There are a lot of hidden assumptions behind any causal interpretation applied to regression coefficients, and the structural equation modeling framework brings those to the foreground and requires you to be quite explicit about what assumptions you're making. A lot of structural equation modeling involves very complex models, but it's also the case that once you're used to thinking in this framework, that it turns out it kind of opens your eyes to the possibility that certain kinds of effects can be estimated with simple models, and that certain practices that we have adopted by habit, especially trying to include as many predictor variables as possible, is not always necessary. And sometimes it may even be misguided. And there'll be a little bit of a demonstration of empirical applications, just a hint. And let's get going on. So what are some of the conclusions that we're going to move to as we work through these slides? And so one is that even if you never use the methods, if you gain some knowledge about structural equation modeling, it can benefit you. And I think it wouldn't be surprising at all that it would benefit you if you're doing quantitative modeling, but it may be less obvious that it also applies to every kind of analysis, including qualitative analysis of every kind. And I'll just expand on that point for a moment. In quantitative analysis, when you go to the SEM framework, it makes you bring hidden assumptions to the foreground. So you have to think carefully about your measurement model and all of the assumptions that lie behind using the measures that you have. In regular workaday research, we often let those things slide into the background, and that can be dangerous. It's certainly convenient, and we need to do it from time to time, but it allows us to become comfortable with assumptions that maybe we should not be so comfortable with. And this is where it applies across the board. Any research that you do, quantitative or qualitative, is going to involve measurement. Measurement is a hard process, and thinking about issues in measurement is going to bring important perspectives to your interpretation of findings and the associations among variables that you may find. And if you're doing qualitative analysis, you're not exempt from this at all. And if you were to move to a formal presentation of your measurement model, you'd be subject to the same critical perspectives that would apply to a quantitative measurement analysis. There's nothing about the qualitative process that gives you King's X on measurement issues. So one of the things that structural equation modeling as a framework does, even if you never use it in any formal way, it kind of trains you to express theory in a way that reveals makes many things explicit, and it makes you think about your empirical analysis in more careful ways. Some of the tools used in developing models in the structural equation modeling perspective draw on graphical representations, and those graphical representations can be really helpful for any kind of analysis. The graphical representations are heuristics which can take your thinking and give them a visual representation, which often makes it easy to see, oh, there's gaps in my thinking, or there are ways to elaborate this, or So just using the graphical tools sometimes can be useful, even if you never go on to quantitative analysis. And then if you do use the perspective directly, the opportunities for quantitative refinements are really quite numerous, and so that they will take you into opportunities that simply aren't otherwise available. And then some specific things. If you begin thinking about your problem from the point of view of structural equation modeling perspectives, you'll have to think explicitly about measurement, and you'll have to make explicit the assumptions that you're making about the measurement error in your observations and so the scores, in quantitative analysis, the numerical values that you attach to variables on a given case. In qualitative analysis, the meaning and interpretations that you assign to labels that apply, or anything. So measurement error is always out there, always lurking as a significant concern, and the habits of structural equation modeling just have those always in the forefront. The same thing is true with regard to thinking about how different variables relate to each other. In regression analysis, we're frequently going to have many independent variables, and we typically learn to estimate a single equation with one y variable, one dependent variable, and several x variables. Thinking about how those are all connected to each other is not necessarily required. The main thing that's kind of required is that we think about how x's relate to y's, how the independent variables relate to the dependent variable, but we are not necessarily obligated to think carefully about how the x's relate to each other. In the SEM perspective, you have to think about that. In ordinary workaday research, where we're estimating single equations, we often don't think about how x's are related to each other, and that's actually a fault. We should think carefully about that. So relating to that is the next point, the distinction between control variables and mediating variables, or controls and mediators. And the reason that distinction is important is that a control variable must be included if it's important, so that you can see the true effect of some independent variable of primary interest. Well, all variables that are involved and have associations with the x in question and the y in question are not necessarily control variables. Some of them may be mediators, and then it's a choice as to whether you should or should not include them in a particular regression equation. If you include them, it changes the kind of effect that you would estimate for the other x's. If you omit them, it changes the effect that you would estimate. And both effects would be relevant for a full analysis. And it's important to know when you are choosing to look at one type or another. And that takes us to the next point, which is distinguishing between direct and indirect effects. Direct effects are effects of x's net of controls. Indirect effects include effects that are transmitted through mediating variables. And then it becomes a question of whether your analysis includes mediators as control variables or not. If you don't include them as mediators, you may get one estimate of the effect. If you do include them, you get a different estimate of the effect. In the SEM approach, you'll estimate multiple equations, whenever you have mediating variables. And you will be able to simultaneously look at direct and indirect effects, and they'll all be evident from the way the model is formulated. And the last item is that you can go way beyond single equation analysis, and without getting into it in great detail, there are opportunities that arise if you can look at a system of variables and how they relate to each other in complex ways. It may give a better expression of a particular theory and allow for more advanced testing and for more appropriate estimation of effects. Single equation analysis is definitely easier, and if it's framed properly, it's all to the good. But sometimes single equation analysis is not enough. So when it's not enough, one of the possibilities you can turn to is the structural equation modeling perspective. So what am I assuming here for this discussion? And I'm assuming very little, only some familiarity with multiple regression analysis. So we're not going to get deep in the weeds. We will look at a few things to give you a flavor of what's involved in structural equation modeling, but we're not going to look at them carefully. We're going to just say, if you want to learn more about the details of structural equation modeling, you'll really have to dive deeper, probably take a course. If not take a course, you'll need to probably attend some workshops that are more than just a half-hour presentation, and you'll need to invest some significant time. So the goal here is not really to learn structural equation modeling. The goal here is to raise awareness about what's involved with the methods, what you can accomplish with it, and gain some appreciation for whether you want to learn more or not. So what actually are the distinctions? And so structural equation modeling can be described as a broad modeling framework that allows researchers to investigate an expanded set of issues beyond what you could consider in regular or standard regression analysis. So one is that it allows you to formulate and estimate and evaluate measurement models. Measurement models for dependent variables, measurement models for independent variables. These are typically taken for granted in regular regression analysis, and that is typically a mistake. We do take it for granted in our regular work, but it's better for us to always have measurement models in mind. If we do, it will cause us to be much more circumspect in the way we think about our findings and how we draw conclusions. In this framework, we can simultaneously assess direct and indirect effects without having to make radical changes in the way we formulate the model. If we're doing single equation analysis, any single equation specification is going to let us see one kind of effect, and we'd have to reformulate the analysis to move between searching out direct effects and indirect effects and total effects. In the SEM approach, it's all there within the same analysis. The last two bullets under this heading are some things that we can do in structural equation modeling that are just not possible at all in the single equation approach. You can look at reciprocal causation between two variables, and you can go beyond that, and you can look at feedback loops within systems of many variables. And a feedback loop, could be considered just a complex way that there's reciprocal causation, but these things they make sense in the real world. They make sense when we think about what we're doing, when we manipulate policy, when we use policy to manipulate the world, we should be thinking about how this may set off chain reactions of effects where there may be reciprocal causation or there may be feedback loops. And in the worst case analysis, if we haven't thought about those things, we may get unexpected consequences when we intervene and try to implement policy based on findings from a single equation analysis. So putting it bluntly, if we're guided in our thinking by the results of a single equation analysis, which is not particularly thoughtful, we might come away thinking that we have knowledge that would allow us to intervene in social policy, take some action, and get an expected effect. And then that may, or if we really were to have that opportunity, it may be that the effect that we get is not what we anticipate because our modeling framework was not thoughtful enough. And this was certainly common in the 1960s and 70s when quantitative modeling first came to the social sciences, and policymakers were often persuaded by social science researchers who were pretty excited about the new methods and the opportunities that people thought were being created to intervene in systems, take actions, and get anticipated results. And it often turned out that policy interventions did not deliver what was expected, and that led to a backlash against social science work. And the only appropriate response is to do better. You can't say, oh, we didn't get the result we promised, and nevertheless, give us the levers of change to manipulate again, because the goal is worthwhile. That people don't buy that. We need to work harder to convince policymakers that we understand the phenomena well enough that if we were to intervene in a system, it would produce consequences that we could predict, and it would not produce unexpected consequences. So what's the distinction between path analysis and structural equation modeling? And there actually may not in the final analysis be a fine distinction, but there's a working distinction. There are elements of path analysis which are quite simple in comparison to the full structural equation modeling framework. But the history of structural equation modeling is that it emerged as an elaboration of path analysis. So it could all be seen as one framework. But if we take the early steps, the beginning steps of structural equation modeling and call that path analysis, then it's something less complex. It's much easier to learn and apply. So it's a good stepping stone for using the simpler methods and then becoming aware of what's possible with structural equation modeling and moving into that. So let's just stop for a second and take a look at what do I mean by regular single equation regression. Well, on the left-hand side, you've got a dependent variable y. On the right-hand side, you've got one or two or more independent variables, x's. It's all set up to estimate how y's vary across values of x's that may be interpreted in terms of effect, maybe even as cause and effect. And the formulation really doesn't make much sense if you're not willing to entertain that. And the effects are directly captured in the regression coefficients, the b's. Okay, well, that's all well and good. And, hopefully we have appropriate caution whenever we estimate a basic multiple regression model. This could be the standard multiple regression model where all of the variables here are interval level variables, and it could be an OLS regression. But the general idea it would apply to logit regression, multinomial logit regression with categorical dependent variables. It could apply to count regression and a wide variety of single equation methods, which have different kinds of dependent variables and various kinds of X variables. It's all still a single equation analysis. There's a lot going on in those models, which is often kind of relegated to the background. And in fact, anytime you run a regression and interpret it, you are embracing a number of assumptions. Often it's implicit, meaning that you don't stop and state explicitly that you're adopting these assumptions. They're just taken for granted. And often it can slip your mind that these things are implied anytime you draw an inference out of the analysis that you've performed. So let's just start with some major unstated assumptions. The variables in the analysis are measured without error. Okay, well, that's kind of a big hardy har. Nobody, if forced to, in front of their dissertation committee or an audience of professionals, would say that your measures in your data set are all without error. You know, that's just indefensible. That would show a tremendous lack of appreciation for how hard measurement is. But nevertheless, when we interpret the effects of coefficients and we think that that relates or corresponds to the real world, that kind of interpretation requires that we assume the variables are measured without error. Another assumption is that the single equation analysis reveals all that's relevant to our question, and that may or may not be true. So the main concern in the single equation approach is how do we specify that single equation? And we may worry about specification issues like, should I include nonlinearities and interactions? And definitely those are all important things to think about. But there are other kinds of things which we often are not thinking about. And one of them is whether the X variables are related to each other in ways that are causal rather than spurious. If they're related to each other in causal ways, it has potentially very dramatic implications for how we would interpret the findings of the regression. And it would have huge implications potentially for how we think about our analysis might correspond to policy consequences if we were to actually try to intervene and change the world based on the knowledge we get from our quantitative analysis. So that takes us to the next point, that we're assuming there are no causal associations among the X's, and that often is highly debatable. Often it's just flat out wrong. And if it is, we need to always have that in the foreground, and it will have a big impact on how we think about our results. So the next bullet point speaks to that. If we think the B's reflect the impact that a change in X will have on Y, it requires all those assumptions above to be true. And that may or may not be the case. We're also assuming that X's affect Y and Y doesn't act back on X. That can be questionable. So that means there's no reciprocal causation. And so reciprocal causation would be simply saying, or focusing more narrowly on, does the Y ever act back directly on X? Sometimes it does. And then there's another way of thinking about it. Could there be a feedback loop? Maybe Y doesn't act back directly on X, but maybe it acts on some other variables, and they in turn are causally connected to the X of interest, and that creates a feedback loop, which means that in a broader way, there is a reciprocal effect. So if those things are ever plausible, it would cause us to think carefully about drawing implications from a single equation analysis, and we might need to consider going to structural equation modeling. Another thing we assume is that errors are uncorrelated. And in OLS regression, we often do think about how errors are correlated, but that's usually at the level of individual observations. And we're thinking about autocorrelation, maybe spatial autocorrelation or time series autocorrelation, and sampling issues like using multi-stage probability samples causes errors to be clustered. So that's one set of thinking about errors that you do think about in single equation models. But here in this context, we go further and we think about how errors associated with measuring the x's and the y's may be correlated, and that can then lead to the findings of the single equation, any particular single equation being distorted by these factors. And so it's a broader way of thinking about errors being connected across not only variables, but measurement process and model specification. Okay, the last thing on this page is that when we run single equation models and we do not state these assumptions, we are nevertheless implicitly asserting them, at least if depending on how we interpret the results. If we interpret them in the usual way, the textbook way, a 1 unit change in X produces a unit change in Y that is estimated by the coefficient B. That interpretation cannot be made without asserting all of these unstated assumptions. And they're not tested, they're asserted. Testing them is hard. When we think about that, we often are left righteously understanding that, well, some of those assumptions may be questionable. If we move the analysis into an SEM framework and give an explicit representation of these assumptions, then we are in a position where we are taking everything a little more seriously, and we have a framework for discussing whether we want to make these assertions or not. And if we don't know quite what to do, we can also do exploratory analysis to explore the implications of these assumptions, kind of robustness checks, if you will. So when we move to SEM, what we're making explicit is that, hey, maybe the variables are measured with error. If they are, can we represent that? If we can conduct a more powerful informative analysis. Hey, maybe the independent variables are connected via causal rather than spurious associations. If they are, we can potentially refine the analysis and get more out of it. We can get a more correct set of findings and a more informed set of understandings about what's going on. And in particular, we think about X's as having implications for Y that go beyond the B in a regression equation. It may include direct and indirect effects, and together they will define total effects. And that may be of interest. We may be particularly interested in a direct effect. That if so, we may get by with a standard regression single equation specification. If we're interested in indirect effects, we're going to have to look at multiple equations. And if we're interested in total effects, then we're going to have to look at the full framework to be able to put together direct and indirect effects to get total effects. And there may be what is called a non-recursive model involved. That is, a non-recursive model is one that would include reciprocal causation and or feedback loops. And if those are present, they can be modeled. It's not easy, it takes hard work, but they can be modeled. And then that we recover one, better estimates of effects, and a lot of insights and implications that could never be understood by simply estimating a single equation regression. The same thing with errors that are correlated in various ways. The SEM approach allows potentially for modeling them in ways that are not possible in the single equation approach. So what is involved? How do we get from single equation to regular regression approaches to the SEM framework? Well, the first thing, I don't know if it's the first thing, but a thing is that you will estimate a structural model. And a structural model is roughly analogous to what you're doing in regular regression. It's just that you're thinking about things more carefully. So in the regular regression, we just look at our observed variables and we treat them as if they are exactly representative of the underlying conceptualization we have of the variables in the analysis. And earlier when I said that, I introduced the critique known as the Hardy-Har-Har critique, which is that when you state it out loud, it becomes completely indefensible. So if we say all of our observed variables are measured without error, and therefore we don't need a measurement model, and we don't have any issues there, you just can't say that out loud in front of knowledgeable people. They will not accept that. You know, you could say, we're going to go forward with this analysis as if we had measures that were accomplished without error as a practical concession to getting the work done. And that might be accepted. In fact, it's routinely accepted, but it implies then much more humility about your findings and your results. So the more formal way is to say, we have observed variables and they are related to true concepts that can be termed latent variables. So we have an indicator that we have measured, we have an observed variable. It stands in for the true concept, which we call a latent variable. The latent variable is pure. It's the concept. It represents the thing that we are truly interested in, that we're trying to capture with our measures. The indicator is our attempt to get an empirical assessment of the latent variable. And when we understand it that way, we always assume that the indicators are flawed. It's very implausible to suggest that the indicators are all perfect representations of the latent variable. So in SEM, structural equation modeling, we just assume this from the very beginning, and we never believe that the observed variables are pure. We're thinking of them as flawed representations of the unobserved latent variable. The latent variable is never actually in the data set. It's an imaginary, ethereal concept. But in our framework, we're going to be estimating the latent variable by making explicit our assumptions about how the latent variable is connected with the observed variable. So that means that we will then be thinking carefully about something called a measurement model. And the measurement model concerns how the latent variables are connected with our observed variables. if we're successful with our measurement model, then our structural model will be estimating relationships between latent variables. And that will be, quote, the true score relationship, the relationship that occurs if you had the true values of the concepts you're trying to measure. If you had accurate latent variables, then the structural model would be the coefficients you get when you regress a latent y on a latent x. In your regular regression, you're regressing an observed y on an observed x. And you're taking that as a stand-in for the true structural regression. In structural equation modeling, we make all that explicit. So we must represent our assumptions about the measurement model. And in regular regression, in SEM, there's a measurement model for every latent variable. And in regular regression, if you have a y variable, it implies that there's a true latent version of it, a latent variable version. And you would have, in the SEM framework, you would have a measurement model for that particular variable. It might be a single indicator model, it might be a multiple indicator model. It may be a complex model, it may be a simple model, but there will be a model. There'll be some model that relates your observed variable in the data to the latent variable, which is the ultimate goal that you're trying to achieve. In regular regression, there's no analog to that. In regular regression, you've got your x's and y's as found in the data. And there's nothing to mediate the relationship between the observed values of x's and y's and your underlying true conception of the latent variable they stand in for. So it's just unexamined. The measurement model is unexamined in regular regression. What is implicit is that you have perfect measurement. So that's the Hardy-Har assumption, which in SEM, you can't let that sneak up on you. You'd have to state it out loud and make it explicit. So within this framework, within the SEM framework, your observed variables are seen as produced by the latent variable. That is, the observation that you've made, the measured x, the measured y, comes about and is created by the existence of the latent variable. So if we measure education, we have the concept of education, and we think of that concept, the pure conception of education, as somehow being embodied in the measurement of education that we achieve through some explicit measurement process, like asking somebody how many years of education they've completed, how many years of schooling. Well, if we view that as a measurement process, we somehow are saying that the underlying idea of education is expressed through the observation. And we should be thinking about it that way. We don't think about the observation creating the latent variable. That's backwards. We hope that the true variable, the latent variable, is producing the observations. Then the last thing that really separates the SEM perspective from regular regression is that all of these models, the structural model, all of these two models, the structural model and the measurement model, are estimated simultaneously in a system of equations, measurement model equations, structural model equations, and these may or may not have There may be single equation measurement models. There may be single equation structural models, or they may involve stages, multi-stages of structural models. Okay, we're keeping this all very abstract. Let's start getting into practical things. How would you do all this? Well, you're not going to do it by using OLS regression procedures that you learn in undergraduate and graduate first courses in analysis. You'll have to use specialized software. There's a bit of history here, and I'll glide over this, but I learned to use structural equation. I learned to estimate structural equation modelings using a program called LISRO, and it's an acronym for it's come to mean a set of strategies implemented in software, but it's just a name for a program. In the earliest days of path analysis, advanced path analysis, and structural equation modeling, there was a blurred line between the two because there was no software. And in the early days, which my history as a sociologist overlaps with those days, you would do things literally by hand by manipulating terms like covariances. A covariance is just a term that you can get from looking at a correlation matrix, or if you estimate a correlation matrix, you just do a set of correlations among X's and Y's all together. Beneath that is the covariance matrix. The correlation matrix is the standardized version of those associations. The covariance matrix is the same set of associations, but it's expressed in metric form, that is, using the scales of the variables. And we would take those terms in the covariance matrix and think about how they were connected to each other, and we would do manual calculations. This is while we were walking uphill in the snow both ways, to school and from school. But we had to do all that, and then LISRO came along and would automate some of those calculations. And so it turns out that LISRO had a very well-deserved reputation for being completely horrible. It had obscure notation. The syntax of the model expression was unbelievably obtuse. That is, it was really hard to look at the implementation of the syntax and understand the model. You literally had to chart it out on a piece of butcher paper to figure out what the heck was going on. And then it would fail. You would try to run a model and it would fail, and it would give you some error message that was completely unhelpful. And even when you did everything the right way, the estimation routines were fragile and it might not work. But in the end, it did sometimes work. And from the perspective of doing everything by hand, this was much nicer. And so LISRO was great. And then along came programs that you might call second generation programs, EQS, AMOS, CALIS, M+. Those were all programs that would often be used in place of LISRO. LISRO evolved. Later versions of LISRO got better. And so the early days, thankfully, don't have to be repeated anymore. And then I'm going to talk a little bit today about the SEM procedure in Stata. And it's not the only example, but I would call it possibly third generation. And the third generation software gives a lot of attention to creating aids for making it possible to build models a little more easily and to obtain estimates easier. And the software is just so much more improved so that it handles problems that previously you would have to deal with by hand, and it's more robust. It doesn't crash as often. You don't have to do tricks to make it work. So the software is getting better. And I'm mentioning this because you cannot do SEM as a practical matter without learning to use some advanced software. And that advanced software, if you get into it, you'll start seeing notation like this. And because LISREL was the first approach, the LISREL representation of the structural equation model is widely adopted, and the authors are the people who invented that analysis framework adopted Greek letters. And it's a blizzard of Greek letters: eta, psi, zeta, epsilon, delta, lambda, theta, epsilon, theta, delta, beta, gamma, psi, phi. So we all are now in the sorority fraternity world. And what can we say? We don't have to know these things to run regular regression. Why the heck do we need to know them now? Well, we need to know them now because regular regression imposes assumptions on all of these terms, which reduce the model from being very complex to being very simple. In the process of doing that, going from the complex to the simple, we may be running roughshod over the truth. We may be running roughshod over reality. And by expressing the full model in all its complexity, even if we just do it as an abstraction, as a theory exercise, it provides a framework for talking about the assumptions we're making and then understanding how those assumptions make these various measures, these various terms collapse into simpler terms. Okay, and I'm not even going to review all of these today. We could talk about these. Let's see, if we look down here where there's something called, we see beta. Beta is where we would get something like regression effects, and that would be structural. It'd be the one way to think about it is that you estimate the structural model, which in SEM, the structural model is a relationship between latent variables, which remember are imaginary, they're true. And we have indicator variables in our data set. So the way the latent variables are connected, that's expressed through coefficients in the beta matrix and the gamma matrix. And the difference between those two is in whether or not a dependent variable is only a dependent variable or whether a dependent variable sometimes is also a predictor. And in this framework, dependent variables are known as endogenous. They are caused by other variables. And variables that are only X variables are called exogenous variables. They are in the analysis, but they never are taken as dependent variables. And then some variables can be both endogenous and exogenous. And that takes us to this formulation. So I'm just going to glide over this stuff because we can't do it justice. But in our data set, we have measures that can be thought of as Y's. They're somewhere at some time going to be taken as dependent variables. We have other variables that are taken as exogenous. They're only going to be predictors, never dependent variables, never endogenous. These are the observed variables. If a variable is a latent endogenous variable, we give it a new symbol, the Greek letter eta. And if it's a latent predictor variable, we give it its own special label. And I always have to stop and think about what is that little critter? That is psi, KSI, okay. my memory on these fails from time to time. So what we're going to have is we're going to have relationships between observed variables over here, across the bottom, starting with endogenous variables. There'll be etas, the latent version, and then y's, some set of observation variables, observed variables, which are the components that are related to the latent variables. We'll have the same thing for the exogenous variables. And then we have a set of error terms, both for the observed variables and for the latent variables. And so there's a framework for thinking about how those are connected. I'm putting this all out here not to freak you out, but just to say that this is what it takes to move to a framework where we can think about everything that's going on in a full model. And that gets us to the basic the basic structural equation is this: a set of this is a matrix notation where the capital B matrix is a matrix of coefficients that capture effects on latent endogenous variables. Those are the regression coefficients we're trying to get. And then there's another set of similar coefficients for other variables in a system of variables where we're getting exogenous coefficients that are determining the values of the exogenous variables. And you don't need to follow all this at this time. And if you go into this representation is found in stated documentation, go to methods and formulas, and you'll see not only these terms laid out more carefully and in more detail, you'll see some other terms which I'm skipping over. And I guess I'll stop now and say, just don't get freaked out. It's just regression in the end. It's just regression only. It's now regression that we're thinking about more carefully. And every part of the analysis, when you break it down into its element, can be understood. It's just like when you start off with simple correlation, and then you move to multiple regression, it looks like things got really more complicated when you start looking at how a regression coefficient is calculated. The way it's calculated in bivariate regression is a pretty simple set of calculations, sums of squares, sums of cross products, do the calculations, look at, plug them into a formula, out comes your B estimate, all is well with the world. And then when you want to go to multiple regression and estimate effects that are net of controls, the calculations get a little more involved. But when you break it down into steps, each step is intelligible, each step makes sense if you spend the time to understand why it's being done. And the same thing here, that there's a lot going on here, but each element of it can be understood in its own right. And you can zero in on that, come to understand it, and then you can back up and see how it plugs in to the broader set of calculations, and all will be okay. In the meantime, before you become an expert on all that, there's a way of using the framework without getting bogged down in all the calculations, and that is to use a graphical representation of the framework. And I'm going to advance. So here's a graph. And this is a graph that, if you understand it, implies a handful of regression equations. And they are being estimated not as literal OLS regression equations, but as equations that are more complicated, but they are directly analogous to estimating a handful of OLS regression equations that are connected to each other. That is, the individual equations are going to be looked at as a set of equations, and using the set of equations will allow us to understand things that we could see without that we could not see if we were using a single equation approach. So there are conventions here which make the graph intelligible. So latent variables, and these are conventions, and the conventions emerged through the habits of researchers and methodologists. So they're not, if you go back, especially in the literature, you'll see conventions emerge over time, and some early presentations don't follow contemporary conventions. It's all the same if you understand it, but it can be frustrating if you're expecting to see things presented one way and the early literature presents it another way. But in the contemporary literature, there's pretty consistent that a latent variable will be represented by an oval or sometimes by a circle, and often that will be a circle or an oval that has a thick border. Okay, so a latent variable is also, we noted earlier, indicated by a Greek letter. So eta 1, 2, and 3 are inside these circles, so those are latent variables. That's the underlying concept that's being measured. We'll go back. An indicator variable is represented by a square or a rectangle. Sometimes people will go to some pains to make sure that the lines are thinner. And so where we have the y's and the x's, we have little rectangle squares. Here, the distinction with the lines is not maintained. Here, everything has a fairly thick line, but a square means that's an observed variable. The oval means that's a latent variable. So let's take a look at what we've got here. And let's see if I can do something useful. So let's take our ultimate dependent variable is eta 3. That's a latent variable. In our data set, we have multiple indicators. That is, we have two, in this case, two observed variables which are being used to represent the latent variable. And now we have another element in the graph that we need to talk about. Okay. And that is causal effects, which are straight lines with arrowheads. And notice that we have a straight line coming from the latent variable to the indicator. That means that our observed variable, the y variable that is measured in the data set, is seen as being a product of the underlying true representation of the concept. So if we're lucky, the existence of the latent concept out in the real world is expressed in the indicator. The latent variable has caused this indicator to take the value it has. That would be because the measurement process captured that connection well. Okay, well this particular model is saying that we have a latent variable measured on the basis of, well, we're modeling how it's connected with two observed variables. That is part of this model. Then we have another let's say, so this is it's represented by eta. Why is it represented by the Greek letter eta? It's because there's a arrow coming into it. It's a latent variable with an arrow coming in, and that means that it is a dependent variable. It's being caused by whatever is at the other end of that arrow. So it's being caused by this latent variable, eta 1. Eta 1 is measured by a set of 3 indicators. So you could think of this as maybe you built a scale. You had 3 questions. You took the responses on those 3 questions. You added them up, and that created a scale. That would be a measurement model where you're imposing some particular relationships between the scores on the 3 variables and the resulting index score, which would be analogous to the eta 1 variable. And in that approach, what you're basically doing is you're imposing a structure on this measurement model. This is a measurement model, and if you say, I'm going to take three observed variables, y1, y2, y3, and I'm going to take their scores and add them up, and that will give me my index score, and that's the variable I'm going to use in my regression. You're essentially saying these are measured without error. They're connected to eta 1 by a coefficient of 1, and the relationship is additive. So you're just adding them up to 1-for-1 correspondence, and the values on y1, y2, and y3 go into eta 1. And so that is a measurement, that's an implied measurement model by that calculation, and that is asserted. It's not directly modeled. In other words, you have said, I'm doing it this way. This is the way I'm getting my value for the latent variable eta 1. That's subject to empirical testing within the SEM framework, and you could see if in a data set the latent variable that you hypothesize is linked to these indicators in the manner that you're imagining as you are hypothesizing. So you could see your measurement, your creation of the index could be seen as a hypothesis for a measurement model. When you actually just go ahead and create the index, it's no longer a hypothesis. You have imposed the result. It's not been tested. It's not always easy to test, but in the SEM framework, if the model is set up in the right way, you can then empirically assess whether the indicators actually connect with the underlying latent variable in the manner that you are imagining. And then this is happening for so here's a measurement model, here's a measurement model, here's a measurement model, here's a measurement model. And each one is subject to evaluation. In ordinary regression, we would be taking our indicators, creating summary measures, maybe an index score, and we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 12 observed variables. We would be using them to create 5 indices. We would then be running regressions on those 5 indices, and we can understand our regressions by looking at the arrows. This index score is predicted by 2 other index scores. That's a regression equation. This would be y, and this would be x1 and x2. We're not going to hang on to that notation because it becomes confusing in this framework. But that is analogous to N3 being a y variable, and I should have said eta. Eta 3 is a y variable predicted by eta 1 and eta 2, which correspond to X variables. And that's it. That's it for the regression. But there's more regressions implied. Here's a regression, and why do we know it's a regression? Because we got two latent variables and they're connected by an arrow. There's only one arrow going into eta 1. So that's a very simple bivariate regression of two latent variables. And here's a second, well, it's actually, I guess, the third regression implied by this graph, and that is a straight line going from what is that, a zeta? I got to go back and think about my Greek letters. Dang it! When I'm doing this, yeah, it's a psi. Okay, so I had it wrong. I'm glad I checked. So that's a psi, and if you're doing it by the book with all these Greek letters, you would say this is an X variable. That's a latent, it's an exogenous latent variable, and that is labeled with the Greek letter psi. Why? Because them's the rules. And the key thing about it is it's never a dependent variable. There's no arrow coming into it with a straight line. So it's only a predictor. It's only an exogenous variable. So N1, or eta 1, I should say, is different. It's both a dependent variable. Hang on. Eta 1 is a dependent variable here, but it's an independent variable here. And in the language, in the notation of SEM, anything that's ever a dependent variable is called an eta. And anything that is never, that's a latent variable, but it's only a predictor, it's never a dependent variable, then it's called a psi, KSY, whatever the pronunciation is for that Greek letter. There are arrows going into psi 1 and psi 2, but there's a curve there and the arrow is double-headed. That's a convention that means this is an association, a correlation. It's not an effect. It's not a regression coefficient. It's a correlation. So its appearance in the flow graph tells you that these variables are empirically associated, and there's something here that is going to be a numerical value, and it can and will be estimated. In OLS regression, that would correspond to a correlation coefficient between two X variables. Over here, we have a coefficient, and this corresponds, that's a beta, and it's telling us how these two latent variables are connected through an effect where eta 1 is impacting eta 3. And that would correspond to a B in a regression analysis. And then over here, we have another coefficient, that's a gamma, and it also is analogous to a B in a regression equation, but in this case, it's how an exogenous latent variable impacts an endogenous latent variable. And the way the gamma and the beta are interpreted is very similar. The difference in the notation is to distinguish how in the overall full model they differ. Eta 1 is sometimes a predictor and sometimes a dependent variable. Psi 1 is only ever a predictor. Okay, well, this model goes into a lot of detail. This graphical representation goes into a lot of detail. There are other things here. If our latent variable has unexplained variation, well, if it's an endogenous variable, an eta, we could think of it as having explained and unexplained variance. The explained variance comes from the variation in eta 1 that comes about from being predicted by psi 1. And then there's an error term that represents its unexplained variation. Every latent endogenous variable, all of the ones with Greek letter etas, have an unexplained component. In OLS regression, that would just be 1 minus r squared. It's what you did not explain. So r squared tells you what you explained in the variation of the dependent variable, and 1 minus r squared is the unexplained variance. And then we do not have that element over here in the exogenous latent variables because they are never taken as dependent variables. So since there's no equation predicting them, there's no distinction between their variation being partitioned into explained and unexplained parts. Their variation is embedded in just overall associations. Okay, we could discuss this model more, but let's move on. And I'm just going to race through some models here. We're coming on an hour and a half, so we're only halfway through the slides. This is just a representation of a measurement model, and we saw it before. This particular model has a lot of measurement models. For every latent variable, of which there are 5, there's a measurement model. Here, we're just looking at one variable, and here's a measurement model. It's got 4 indicators that are involved in the association with the latent variable. And this, you could work, suppose this is very common in social psychology, that you're developing multiple indicators to try to get at some difficult concept like notion of self or identity, or in anything you could imagine. You might have a survey with a bunch of items that you're using to try to elicit relevant information about the underlying construct. And then, if you put them together in a summated index, you've imposed a measurement model. And you could take all of that into an evaluation framework and then try to validate that model. And that would take you into SEM. If you just compute an index, you assert a measurement model. It's untested, it's unconfirmed, it's speculative, it's a hypothesis that goes unexamined. If you move it into SEM, it becomes a hypothesis, and you look for ways to try to empirically validate it. Okay, let's move on. Other models. Here is a graphical representation. The variables are all in squares. That means that they are observed variables. There's no latent variables here. And that means that we're running regular regression. This is a model that comes from the early days of path analysis. And we have a series of variables which are predictors, and we have 2 variables which are sometimes dependent variables. Some of the relationships are quite straightforward. RIntel, R underscore SES, that's R for respondent, F for friend. And we're looking at occupational aspirations as the dependent variable, R for respondent, F for friend. And we're looking at the reciprocal causation. Does one's own occupational aspiration, your goals for the future, affect your friends' aspirations? Do your friends' aspirations affect your own aspirations? And in the stratification literature, it's hypothesized to be a reciprocal relationship, and people were setting out trying to estimate the effect. Can you estimate that in a single equation approach? And the answer is no. Can you estimate it in a multi-equation analysis? Yes. But with major qualifications. You must estimate multiple regressions, not a multiple regression, but two or more multiple regression equations. And a number of special things must be true. So notice two variables on the far left, three variables on the far left have arrows going into respondents' aspirations. And three variables on the left have arrows going into friends' aspirations. And the set of three variables for each of those is not the same set. So there's a declaration here that there's by the graph, this variable does not have an effect on friends' aspirations. And this variable does not have an effect on respondents' aspirations. If that's true, then calculations can become possible, which will allow for these two reciprocal effects to be quantitatively evaluated. So you'll often see this picture float up in introductions to SEM because it was a breakthrough to establish this. This occurred back in the 1960s. And this is being done without multiple indicators. So we have single indicators and we're estimating a reciprocal causation. So that to learn to do this, you'd have to take a course and get down and dirty to see how this all works out. But you will be able to estimate separate coefficients for the separate causal effects in a reciprocal relationship in a cross-sectional data set where otherwise, it would be impossible to estimate that relationship. Okay, here's another famous example from the early literature, and what it brings in is a model with indicators and latent variables. So this is a very influential model developed in the early days. It was first done by hand, and then later, when software comes along, we typically, one of the examples they will implement is showing you how to estimate this using the software. That way you can relate the software to the detailed manual calculations that would be required to do this. The first people who did this did it all by hand. God bless their little souls, because it's really hard. Let's see. What can we say about comparing regular single equation analysis and structural equation? A couple of quick things. Depending on the modeling technique, you could be using least squares regression in single equation analysis. Okay, why is this not working? So you might be using fractional regression, and that would be maximum likelihood. You could be using OLS regression. It would be least squares. When you're doing this in structural equation, it's always going to be maximum likelihood. Not always, but 99 times out of 100, especially when you're first learning. And what can you do? Well, you can evaluate effects. That would be coefficients and whether or not they're significant. And you would evaluate that with T and Z tests, depending on the regression type. In structural equation models, it'll typically just be Z tests because T is a small sample statistic and there's not an analog for it. So that means that structural equation models will rely on large sample theory. So we're going to be using Z instead of T. That means if you don't have large samples, your results are questionable and there's no workaround for that. You just have to live with that uncertainty. Then we come to evaluating the model. In single equation, you'd go to R square or something like it, and maybe the chi-square likelihood ratio test. In structural equation models, you have an analog to that for the full set of equations, and then you can also look at submodels for different variables that are dependent. And so you've got a variety of models and submodels to be evaluated. There's one global model evaluation, and that's an evaluation of all the equations simultaneously. And that's usually important because you gain an ability to test certain things if you're testing the entire model at once. And if you only go equation by equation, you lose some of those capabilities. What's the objective in the empirical analysis? The objective in regular regression is to predict the value of Y for individual cases. In structural equation models, your objective is something else. You're trying to predict the entire set of associations among all of the observed variables. You may be thinking about latent variables, but what you have are associations among observed variables. That's either a correlation matrix or a covariance matrix, a variance covariance matrix. And if your modeling is successful, you will be able to reproduce all of the terms in the variance covariance matrix from your knowledge of the relationships in the measurement models and in the structural models. That's kind of complicated, but there's power and advantages gained. So your predictions in regular regression are the dependent variable. Your predictions in SEM are, was I able to reproduce the variance covariance? And same thing about errors. Let's see. There are simple, we're going to scoot really fast now because things are going to be made simpler. That's the full background. Path analysis takes a subset of things that are simpler, which means it's going to be easier to talk about things. The main thing about path analysis is that you're going to maintain this ability to think about X's and Y's in a complex set of equations, but you're going to be able to run the models primarily using ordinary least squares. And the models may be simple single indicator models where you've assumed that the measurement model is quite simple and that there's no error in the dependent variable. And you're also going to assume that the causal effects are fairly simple, that there's no feedback loops, no reciprocal causation, no correlated error terms. So now we're getting into the kind of model that's implicit when you run an OLS regression, except that now we're going to consider the possibility of having two or more regressions in the same analysis. And let's take a look here. Here's a very simple flow graph of a model that corresponds to an OLS regression. And what we have here, we have 3 latent variables, but each of the latent variables corresponds to a single indicator. So we have a measurement model that says I have one observed variable in my data set, and I'm going to say that my latent variable is exactly equal to the observed variable. And I use uppercase and lowercase to distinguish between observed and latent variable. And so what am I assuming about the measurement model? I'm assuming that the B connecting these two is exactly 1. There's a 1-to-1 correspondence. And regarding this error term, and which reflects the error in the connection between the true or latent variable and the indicator, I'm assuming that the R square for that is 0. The error term does not explain any part of the indicator. The indicator reflects only the latent. So this would be saying the indicators are perfect measures. And what I just reviewed would apply to all 3 variables in the model. And in this particular model, the flow graph implies 1 regression equation, because we have a straight line going into political view, from education, and from OP&E, which stands for opposition to integration. If we go to this model, now we have 2 regressions implied. We have the same measurement model. Every indicator is perfect. We have a single indicator. Each single indicator is a perfect representation of the latent concept. But now we have 2 regressions. We need 1 regression here with education and opposition to integration, both predicting political view. And we have another regression here, where opposition to integration is predicted by education. So the flow graph has now distinguished. So watch this region of the model, and I'm going to go back and forth. Oops. Here, there's no causal connection. This is a curved arrow. Here, there is a straight line arrow. The choice between straight line representation and curved representation changes everything. It changes the way we establish the effects of the variables. So now if we go back, there's notation involved here. I'll just say this notation corresponds to this part of the model. And it's a single effect. And well, let's see, I'm not going to get bogged down in the notation. I'm just looking at the time, and as always, it's incredible how fast it's gone. Let me try not to screw things up. If we imagine a curved arrow here, if we assert a curved arrow, we're asserting there's no causal connection. between those two. So the entire effect of education on political view is embedded in whatever coefficient comes out of this regression. If we assert that there's a straight line here, that means there's a causal connection here, and there's a causal connection here as before, and there's a causal connection previously not seen, which is the compound, there's that channel of effect, education into op-int into political view. So now education has two effects. One is direct and one is indirect. The direct effect is the connection via the straight line. There's a coefficient for that. The indirect effect is the combination of multiplying the B that links the regression coefficient that links education and opposition to integration, and the B that connects opposition to integration and political view. The total effect is the combination of those. And here's where the model framing becomes important. In this model, we have asserted that the education op-int connection is non-causal. So the total effect is just the one arrow. In this model, we've hypothesized or asserted a causal connection. So now there's more effects from education, and the total effect is now larger, potentially. There's simple implications for this. The simple implication is your choice about whether to view this relationship as causal or non-causal means you will assess the relationship between education and political view entirely differently. What is the implication? For every single equation regression you run, you're implicitly assuming all x's are connected by curved arrows, which means they can only have direct effects. You have to stop and think about that. If you said that out loud, could it possibly be plausible? None of my x's are causally connected to each other. Like, this is a very simple model. There are only two x's. What if you've got 8 x's? You would see that in a lot of single equation analyses. Could you say every one of these x's absolutely has no causal connections to any other x? Well, if that's true, then the effect of each predictor is going to be captured just by the coefficients in the single regression, because all of the x variables are connected by non-causal curved arrows. If that's not true, and any two of the x's among the set of x's is connected by a straight line arrow, then the single equation estimate is not the total estimate of effect. It's only the direct effect. And indirect effects are being ignored in the single equation. And this is important because direct effects and indirect effects can be in different directions. So let's say that the direct effect is negative, and these two effects are positive. The indirect effect through the combined pathway is positive, and it could offset this effect. If that's true in a policy analysis and you ran a single equation model, you would be thinking that the effect of education is going to have a negative impact. Raising education is going to have a negative impact. It could have no effect whatsoever because in reality, because the indirect effect neutralizes the indirect positive effect neutralizes the negative effect. Or it could even have a positive effect if the indirect effect is larger than the direct effect. Not only is that possible, it often is the case in analyses that people take seriously. So the movement to thinking about your single equation models in this structural equation framework is not a small thing, even if you never run. So, this model in front of us can be estimated with OLS regression just by running two simple regressions. But the way we interpret it is guided by this picture. And this picture is invoking a much larger framework that is going to guide our interpretation. And we could have chosen an alternative representation within that wider framework. And that alternative representation forces us to draw out different understanding from our regressions. So this is all happening without any thoughtful consideration anytime we run a single equation regression. In your typical single equation analysis, all of this is being assumed implicitly. And if you were forced to talk about it explicitly, it might or might not seem plausible. And that would change everything regarding how plausible your interpretations are based on the regressions that you're discussing. I have got to wrap up rapidly. So let's just say those effects can be estimated by hand, those various direct and indirect and total effects. SEM will do it for you, and that's nice. And there's a little program that I'm going to post. It's not posted yet. I wanted to give you some warning. And if you use SEM, not only do you get the value, but you also can get confidence intervals, and you can perform tests on the separate direct, indirect, and total effects. So that's nice. In SEM, you could, in theory, go back and reevaluate your measurement assumptions. And the ideal would be you would actually test the measurement model. So the har assertion that I made is to say that these assumptions that the measurement, which imply the measurement model is perfect, are hard to believe. But nevertheless, that's what we are implicitly asserting in a single equation approach. It may not be easy to test what the true measurement model is. Measurement models have a framework all of their own, which I've glided over here. But what you can do is that you can use SEM. Well, if you implement the OLS regression approach in SEM, you would have to assert the single indicator measurement model with perfect measurement. You would have to actually type that in to your regression specification and own that assumption. In its place, you could plug in some other assumptions. You could say, what if these variables are not measured perfectly? Well, even if you think they might not be, but you don't know what it actually is, you could plug in hypothetical values to see if it makes a difference. And my example program does that. And very quickly, you can go back and take a look at this slide. But the general expectation would be that if you've measured variables with random measurement error, then your coefficients will be attenuated back towards zero. Random noise in a measurement makes it hard to find the connection between the two variables. If the connection is obscured by noise, your regression coefficient will move back towards zero. If you can mathematically understand the magnitude of that random error, you can use that information in SEM to achieve a correct estimate of the regression coefficient. That's a good trick. And to take that exercise seriously, you'd have to have some justification for plugging in a known value. Okay, so here's what I did. In the program, I took the single indicator model, which is represented an OLS, which corresponds to an OLS regression, and I said it has perfect measurement. And that is the no measurement error model A. And then I plugged in, no, let's say that each one of these variables is measured with error, and it's the best kind of error, best meaning the easiest kind of error to handle, and that each one is but slightly different in magnitude. So let's come down and look down here. When we estimate regression coefficients, what happens? Under the no measurement error model A, we get this set of estimated effects. The effect of education on political view is essentially zero, but it's negative. The effect of education on opposition to integration is negative 0.3. The effect of opposition on political view is positive 0.1. If we plug in these values in the measurement model, some of the coefficients change. The effect of education on opposition to integration goes up. It's now a stronger negative effect. And the effect of opposition to integration on political view goes up. It becomes stronger. It's increased by about 2/3. That means that the direct effect has gone up in magnitude, and the indirect effect of education operating through opposition to integration has also gone up. Those calculations are not shown, but that would be a clear implication. All of the regression effects got larger in size, so the indirect effects, which are based on them, would also go up in size. Okay, well, serious modeling, sometimes we would try to do this. In a more workaday world where measurement modeling is not easy, and we have indicators that we're using in OLS regressions, what would it lead us to do? It would lead us to say, in a very common sense way, I'm running a single equation OLS regression. I'm pretending all the measures are perfect, and the B's therefore represent what's going on. But in a common sense way, I know my measures are not perfect. So I should assume these B's may not be correct. If all I do is simply acknowledge that, I'm now interpreting the results in a more nuanced way based on a broader understanding and a more informed perspective. I'm not running SEM, but I'm looking at my OLS regression in a new way because I'm aware of what this might look like if it were modeled in SEM. Just being able to do that as part of your, just being able to bring that informed background to the interpretation of your single equation results makes you a better researcher. It makes you more cautious about the effects. You could say, well, I could be underestimating this effect. But that would be, if it's a bivariate regression, the presence of measurement error always attenuates effects. You'd be safe with that assumption. In multivariate, it's more complicated. So you'd have to simply say, this may not be the right measurement. This may not be the right effect. I should think about that. If it's important, maybe like policy is going to be based on this analysis, I should take that very seriously and do some more work. Okay, well, at this point, everybody's died and is no longer on the call. Okay, but there's a whole bunch of good things that you can get out of the framework, even if you never use it. And if you do use it, there's even more. And then we have to, always acknowledge limitations. The one is, the first time you learn SEM, you can get a case of religion and think that all problems are solvable. With this new modeling framework, I will correct for attenuation and measurement error consequences, and I'm going to get true results. Well, the problem is SEM only works if you have really good theory. To estimate the model, you will have to make strong declarations about the nature of the framework, the measurement model and the structural model. And those strong declarations may be open to dispute. As long as they're open to dispute, you don't have any faith in the results. You have a set of alternative results, which itself could be useful because maybe the alternatives will show that a certain set of findings are robust across all the alternatives, but more than likely some findings will depend in a critical way on the framing of the theory, which is in dispute. And other limitations, when you're really doing this in a serious way, the modeling is a lot of work. It's good and bad. I mean, sometimes my dissertation supervisor literally told me that he thought it was bad for sociology that software was making it so easy to estimate equations. And his take on it was this: when he was in graduate school, you had to do it all by hand. And you would never run a regression without thinking about it very carefully, because it might take months to implement it. And you had to have a high level of confidence that you were estimating the right equation. And then in my generation, we were using mainframe software, which nowadays you would say is not easy to use. But for him, for my dissertation supervisor, he just said, well, hell, you can run regressions right and left. You don't have to think about them. You can just run them. Then if you like one, you can present that to people and they don't know about all the ones you looked at. And he was horrified by that. And I am too. It's even easier today than it ever has been. And it just means, so when we say SEM is hard, because it forces us to justify all of the assumptions that we're going to have to make explicit in order to run the software. We should have that same appreciation that when we run an OLS regression, single equation, logit regression, or any other kind of model. Beneath the surface, there are all these assumptions that are implicit that we're just accepting without question. And if we moved into the SEM framework, we'd have to justify them, and it would not be easy. It would be hard. So SEM makes it hard, but we really shouldn't see that as a fault of SEM. We should see that as a criticism of our regular everyday work habits, that we get habituated to glossing over those assumptions, which make estimating the regression easy. And we ought to be taking the assumptions seriously, which means estimating them is not an easy task. Okay, last bit of advice, take a course. It's a good idea. Sit in a workshop. It's a good idea. Don't expect to learn everything at once. You don't have to. You don't need to. You can still gain a lot from just sitting in and hearing the discussion, even if you never ever run a structural equation model. If all you ever do is qualitative analysis, you would still think, oh, I have observations. My observations are, I may be drawing connections between my observations. In the back of your mind, measurement model, what's my measurement instrument? Me, I'm recording things. I'm writing things down. I'm assigning meaning and labels to these things. That's a measurement model. Can you say it's done without error? Hardy har har comes to mind. There's no escaping hardy har har. Qualitative work is measurements are disputed. Measurements have error. To claim otherwise is to be exposed to ridicule. So just thinking about the framework helps. Another way to say it is it's forcing you to go back to first principles of methodology. And then the last item here, don't be intimidated. You could look at all this and say, I think I'm going to go sell ice cream. I'm going to run a food truck. It can all be mastered if you need to. You may not need to master it to gain benefits from it. And if you do need to master it, you'll be able to do it. It's intimidating if you look at all of it at once, but you'll learn it in parts. And when it's broken down into elements and step by step, it becomes intelligible. And while it's always complicated, it can always be worked out step by step. Okay, what did that run? 2 hours. I only had 33 slides. I was certain I would get this done in 45 minutes. Okay, that didn't happen. So I don't know. Do we have enough tape to go for 2 hours on the recording?